So dear students, now we are continuing functions where we have stopped in the previous class. We have stopped at one function example. Now we are continuing that. So functions, continuation to functions, right. So on to function we have discussed successfully. Coming to the next point, bijective function. So bijective function. So a function f from a to b is said to be bijective function if it is both one and onto function. So in a single function, if you are seeing both one function and onto functions simultaneously, then it is called bijective function. Bijective function plays important role among the functions chapter. So f maps a to b is said to be bijective function f maps a to b is said to be a bijective function if f is both one and onto function. One and onto function. That means both functions rules you have to see simultaneously in the same function, then it is said to be bijective function. See, I will give an example. Say AB, say this is 1, 2, 3, 4, so this is 5, 6, 7, 8, for example only. Now here I am taking a function, you justify whether it is bijective or not. So this is a function. This is clearly bijective function because you see it is obeying both one function rule and onto function rule at a time. So it is clearly bijective function. So yes, this is bijective function. Understood? Now let us take another function. Same sets, let us take a and b. 1, 2, 3, 4, 5, 6, 7, 8. See, this is another function g here. In codomain, the element 7 is left over without any preimage, so it is not onto as well. It is even not 1 also, you see. Two different elements of A having same image. So this is neither 1 nor onto. So it is not bijective. So even one function rule is successful, another function rule is, but that means say for a moment one function is rule, one function rule is successful, but onto is not successful, so it cannot be bijective. If onto is successful, one is not successful, not bijective. Both are not successful, not bijective. It is bijective if and only if you are seeing both functions rules, one rule and as well as onto rule, you have to see simultaneously. So now I am taking an example, and whether I am going to prove that it is bijective function, that this procedure is very important, you please observe. See, the question is if R to R is defined as f of x is equal 5x plus 4. Show that f is bijective function. So now how we'll prove? You see, solution. So first let x1, x2 belongs to R. Therefore f of x1 would be 5x1 plus 4. F of x2 would be 5x2 plus 4. Now consider f of x1 is equal to f of x2. So this implies 5x1 plus 4 is equal to 5x2 plus 4. That 4 and 4 get cancelled. 5x1 is equal to 5x2. This 5 and 5 get cancelled. x1 is equal to x2. So as f of x1 is equal to f of x2, we are seeing x1 is equal to x2. That means, as we have discussed in the previous class, so this is obeying the 1-1 function rule. So therefore f R to R is 1-1 function. Right? Now let us see the bijection. To see bijection, you have to even see onto, because already we have verified 1-1, you have to check onto. If you have even checked onto successfully, you can conclude bijection. It is bijection. So I am verifying whether f is onto function or not. So now let us take the function in arrow diagrams. So this is a R domain, here R. This x maps to f of x, where it is equal 5x plus 4. So now in order to be onto, now what you have to take is, you have to choose an arbitrary element y in codomain, and that y when equated to 5x plus 4, the corresponding x which you are getting, that should fall in R, in the domain R. If you could prove, so you have proved that for y there is a preimage x in R. So you can conclude it is onto function. So now let y belongs to R be an arbitrary element in codomain. And let y is equal 5x plus 4. So this implies y minus 4 is equal 5x, implies x is equal y minus 4 by pi. So as y belongs to R, y minus 4 by pi belongs to R for all y belongs to R. So what does it mean? The x belongs to R, because y minus 4 by 5 it is nothing but x, so x belongs to R. So you could get 1x as pre-image corresponding to each y in codomain. So here you could prove that onto relation. Therefore here you could see f of x is equal to y for an arbitrary y belongs to R. So therefore you can conclude it is onto function. So this is 2, that previous one is 1. From 1 and 2 we can conclude f is both 1, 1 and onto. So f is bijective function. So next, coming to bijective function, the important definition is inverse function. Inverse function. See, inverse function of a function exists if and only if the given function is bijective function. So only for bijective functions inverse functions will survive. This is most important point that you have to understand. Only for bijective functions we can write inverse functions. So please observe the bijective, this inverse function definition carefully, which I am writing on board. This definition is most important. So many students will have some or other confusion with respect to definition of inverse function. Now I am making it very clear. Please observe. Follow point to point. See, f maps A to B is a bijective function f maps A to B is a bijective function defined as f of A is equal to B, where A belongs to A and B belongs to B. It is possible because it is bijective. Then a bijective function, again a bijective function, a bijective function G, this time this is from B to A. See this, you please observe this carefully. F is from A to B, G is from B to A. So a bijective function G from B to A, which is defined as G of B is equal to A then G is said to be inverse function of F. And using symbols, how do you denote? And is denoted by G is equal F inverse. So hereafter the inverse function of f is denoted by f inverse. So I will explain this definition. Please observe carefully. When there is a bijective function f which maps a into b, it is a bijective function and is defined as f of a is equal to b. Then under this circumstance, if you take a bijective function g from b to a with the definition g of b is equal to a, see, please understand that is f of a is equal to b and this is g of b is equal to a. Then this bijective function g from b to a is known as inverse function of f, and inverse function of f hereafter is denoted by inverse f. Understood? Now I will take a small example and I will make you understand with an example. See here. See, suppose a is equal 1, 2, 3, 4. Say b is equal, say p, q, r, s, something. Only example, no? Now I am taking a bijective function f from a to b. How I am taking, you see. So like this I am taking. So here f is clearly a bijective function because it is satisfying both 1 function rule and onto function rule simultaneously. So it is a bijective function. Then define inverse f. So how you will define inverse f in this case? So obviously inverse f is from b to a, where b is p, q, r, s and a is 1, 2, 3, 4. So here p to 1 you have to take, q to 2, r to 3 and s to 4. This should be f inverse. So now I think you have understood what is f inverse, right? Suppose f itself is a not bijective, so you cannot talk about its inverse function. So under that case, when f is not a bijective function, you have to write inverse f does not exist. This is a very clear-cut point that you have to understand. So now coming to the next type, which is identity function. Identity function. This is most important in functions. So in a usual function, that function will be from like a to b, c to d, like that. But in identity function, it will be from a to a or b to b or c to c, like that. So a function f from a to a. So this identity function always will be on a single set. So a to a or b to b or c to c, like that. A to b identity function will not be there. So please do remember this. So a function f maps a to a is said to be identity function if and only if f of a is equal to a for all a belongs to a. That means under the identity function, the image of one element will be itself. The image of one element will be itself. One will have one only as image, like that every element will have the same element as image. So that kind of function is said to be identity function. Understood? Now let us take an example. Some a to a, suppose a say 1 2 3 4. So obviously here 1 2 3 4. Now if you define a function like 1 map to 1, 2 map to 2, 3 map to 3, 4 map to 4, then that function would be the identity function. Every element image is itself. So this is clearly an identity function. Identity function. Now let us take one function which is not identity so that you will understand more clearly. Here you see a 1 2 3 4 1 2 3 4, say 1 to 2 2 to 2, so 3 to 3 4 to 4. So this is a function g. It's clearly not identity function. Of course it is a function, but not an identity function, because one has the image 2. In identity that situation will never happen. One cannot have 2 as image in identity function. I am saying in identity function one will have the image 1 only. Understood? So now identity function on A is denoted by IA hereafter. So notation. Identity function defined on set A is denoted by IA. So IA means identity function on A, right? Chalo, next function. After identity function, the next function is real variable function. So real variable function. So what is real variable function? Here you see, when f maps A to B and A is a subset of R, set of real numbers, and B is any set, then that function is said to be real variable function. Once again I will repeat, you see f maps A to B is said to be real variable function if the domain A is subset of R and B is any set. Understood? See, I am writing now the definition on board. F maps A to B is such that A is subset of R and B is any set, then F is real variable function. Understood? Now, real valued function. In this case, A is any set, B is subset of R. Understood? So, same definition, you can follow that same footsteps. The only thing is, here A is any set and B is subset of R. So, here codomain is subset of R. Understood? And last, real function. F maps A to B is said to be a real function if both domain and codomain are subsets of R. So, if both domain and codomain are subsets of R, if A is subset of R and B is subset of R, then it is called real function. And in mathematics, mostly we deal with real functions whose domains and codomains both are subsets of R. So trigonometric functions, logarithmic functions, exponential functions, these all are real functions only because they both domain and codomain are subsets of R. So in mathematics we only deal with real functions. So we dance on the real line only in functions. Understood? Now, equality of functions. This is most important point that every student should have to understand. Under what circumstance you will say that the functions are equal. So it is most important. See here, two functions f and g are said to be equal. Two functions f and g are said to be equal. Two functions f and g are said to be equal if and only if, number one, the two functions should have same domain. See, important, most important. Two functions should have equal domains. So, domain of f should be equal to domain of g. And their codomains also should be equal. Second, codomain of f equal to codomain of g. And at last, the values of the functions at each point must be same. That means f of x should be equal to g of x for all x belongs to their domain. So for each and every point in the domain of the functions f and g, which value the function f takes, the same value the function g should take. So if these three rules obeyed, successfully, then those functions are said to be equal, and the equality of functions is denoted by f equal to g and the inequality is f is not equal to g. So, say two functions are unequal, say, then what would have been happened over there? Either their domains may be different or codomains may be different, or the values, the functions which are taking at certain point may be different, so that any of the three may be failed. So that is why you will say f is not equal to g. Understood? So I will give an example. With an example I will explain. You please try to understand about equality of function, because it is most important in functions. So, see here, I am taking a function n to z, set of natural numbers to set of integers. F n to z is defined as f of x is equal to x minus 1 n to z, and g n to q is rational number, set of rational numbers. Another function g n to q is defined as g of x is equal x minus 1. Now can you say are these functions are equal? No. Here the functions are not equal. What is the reason? They are different in codomains. Rest of the things are same, but they are different in codomain. That's all finished. So as z is not equal to q, as the codomains are different, here f is not equal to g. Did you understand? Now let us take another example. Suppose f n to z is defined as f at x is equal x square minus 3, right? And g n to q is defined as so now here let us take g as some z to r, let us take, or z to z. So f n to z is defined as f of x is equal to x square minus 3, and if another function g from integers to integers, z to z, is defined as g of x is equal to x square minus 3. Now are these functions are equal? No. Why? The domains are different. Codomains are same, definitions are same, but the domains are different. See, the domains are different. As the domains are different, these functions are unequal. So I have to give the same reason. As the domains are different, these two functions are unequal, right? Now coming to another example, third example. f q to r is defined as f of x is equal x cube plus 1 by 4, right? And gq to r is defined as g of x is equal x cube minus 1 by 4. Here also the functions are different. F is not equal to g, because though you are seeing domain same, though you are seeing codomain same, the definitions you see carefully, definitions are not equal. So here, as f of x is not equal to g of x, so you can say here f is not equal to g. Now at last I am taking that fourth example. See, f r to r is defined as f of x is equal x square. G r to r is defined as g of y is equal y square. Here just I change the variable from x to y, there is no any wrong. See here, domain same, codomain same, and their images, see g, that x is mapped to x square, y is mapped to y square. Same, definition wise also same, only variable change. After all, it is running variable, you can change. So all the definitions are successfully satisfied here, domain same, codomain same, definition same, so that you can successfully conclude that here f is equal to g. Understood? I think you understood about equality of functions. So now algebra of real functions. So here some properties which we take without proof as granted. That properties, some of those properties I am writing here. Please see. See, f r to r and g r to r are two real functions. If r to r and g r to r are two real functions, then these following whatever the properties which we are writing, those are taken as true without any proof only. So first one is f plus or minus g of x, which is equal to f of x plus or minus g of x. Now second, f into g of x is equal to f of x into g of x. Now coming to third property, f by g of x is equal to f of x by g of x, where g of x is not equal to 0. Next, some constant added to some function where this k is constant, like 2, 3, 4, 10, 5 by 2, etc. So k constant plus some function, sum of these two, how it is taken, it is equal to constant plus f of x, where k is constant. Coming to, even if it is minus also the same thing. Now coming to product, some constant into some function of x is equal to that constant into function, constant times of the function f of x. Now coming to the sixth property, when k1 and k2 are constants and f of x and g of x are two real functions, then k1 f plus k2g plus or minus, no problem. So k1f plus or minus k2g is defined as k1 into f of x plus or minus k2 into g of x. Understood? Next, seventh property, f power nx, which is equal to f of x whole power n. Right? So these are the some basic algebra of real functions. How do we use these in problems? Here I'll explain, taking an example. Okay? See, here I'm taking an example and I'm solving all the problems. So observe carefully. So the question is f R2R and G R2R are defined as, say, f of x is equal 2x minus 5 and g of x is equal say x square. Say for a moment, then find so here I'll parallelly actually I have to write the questions, but to save some time I'm parallelly writing the question and solving also. Okay? So now first f plus g, find and solve. So f plus g you want first in the first question, f plus g of x. So which is equal f of x plus g of x, as I have defined in algebra of real functions. So this is equal to f of x is 2x minus 5 plus g of x is x square. Right? Then if you write in order, so this would be x square plus 2x minus 5. So coming to next one, say f into g of x required for the same functions. F into g of x is equal f of x into g of x. So whereas f of x is 2x minus 5 into g of x is x square. So if you multiply 2x cube minus 5x square, coming to next, f by g of x, which is equal to f of x by g of x. That g of x should not be 0 here. So what is f of x? 2x minus 5 by g of x is x square. Here x square should not be 0. That means x should not be 0. This is most important point. So fourth one, suppose you want to find 3f minus 4g. Say for a moment. So if you want to find 3f minus 4g, so 3f minus 4g of x, so which is equal to 3 into f of x minus 4 into g of x, right, as I defined. So which is equal to 3 into f of x is 2x minus 5 minus 4 into g of x is x square. So this is equal to 3 to the 6x minus 15 minus 4x square. So that would be 3f minus 4g of x. Are you following? Next. Now suppose if you want to find f square. So f square of x is equal to f of x whole square. And how we have taken f of x? You please take that definition. That function f of x whole square. Understood? Right. So now suppose you want to find g cube x. What is g cube x? It is g of x whole cube. What g of x we have taken? It is x square. We have taken g of x as x square. You see in the definition, of course I wrapped it, but it will be in your notes. G of x is x square whole cube, which is x power 6. So like this, we have algebra of real functions. Okay, understood? Suppose if you want to solve this kind of algebra of real functions problems, okay, with respect to numerical problems, how you will do? I will explain that also. See, suppose f is defined as, say for a moment, 1 4 2 5 minus 3 6. Say next g is defined as 1 minus 8 2 9 minus 3 10. Say for a moment, it is only example. Then let us find, okay, 1 by 1 f plus g. So suppose if you want to find f plus g of x is equal f of x plus g of x. So here x belongs to the domain, this is the common domain of f and g. X belongs to common domain of f and g, which is nothing but 1, 2, minus 3. So now each value you have to pick up from the domain, the common domain of f and g, and you have to find these values. So first 1, next 2, next minus 3. So f plus g of 1 equal to f of 1 plus g of 1. So f of 1 by definition it is 4 here, g of 1 by definition it is minus 8, which is equal to 4 minus 8, which is minus 4. This is f plus g of 1. Next coming f plus g of next value 2. Next value is 2, f plus g of 2 is equal to f of 2 plus g of 2. Whereas f of 2 by definition here it is f of 2 is 5, g of 2 is 9. 9 plus 5, 14. Next coming to f plus g of minus 3 equal to f of minus 3 plus g of minus 3. By definition f of minus 3 is 6 plus g of minus 3 is 10. 6 plus 10 is 16. So finally you have to conclude f plus g. F plus g is equal, now you have to write that function. So it is 1 minus 4, 2, 14 and minus 3, 16. This is the way to find f plus g. Similarly f minus g, f into g, all are same procedure. But I will do one more to have clear understanding. Suppose you need to find 2f minus 3g for a moment. 2f minus 3g you need to find. So 2f minus 3g of x is equal to 2 into f of x minus 3 into g of x. So now first 1, next 2, next minus 3, like same like previous problem. 2f minus 3g of 1 is equal to 2 into f of 1 minus 3 into g of 1, which is equal 2 into f of 1 is 4 minus 3 into g of 1 is minus 8. So 2 4s are 8, minus into minus plus, 3 8s are 24, which is 32. Understood? So next x value you have to take 2. So 2f minus 3g of 2 is equal to 2 into f of 2 minus 3 into g of 2, which is equal to 2 into f of 2 is 5 minus 3 into g of 2 is 9. This is equal to 5s are 10 minus 27, which is minus 17. Understood? Next 2f minus 3g of the next and last value, which is minus 3. This is equal to 2 into f of minus 3 into g of minus 3, which is equal to 2 into f of minus 3 is 6 minus 3 into g of minus 3 is 10, which is equal to 12 minus 30, which is minus 18. Therefore, 2f minus 3g will be set of ordered pairs 132, 2 comma minus 17 and minus 3 comma minus 18. Did you understand? This is 2f minus 3g. Now let us find out one more, root f. So you need to find root f now. Root f of x is equal root over f of x. This is definition. So now root f of 1 is equal root over f of 1, which is equal root over f of 1 is 4, which is 2. Next, root f of 2 is equal root over f of 2, which is root 5. You keep it unchanged. Now root f of minus 3, okay, which is equal root over f of minus 3, which is equal to root over f of minus 3 is 6, right? Therefore, root f is equal to 1 to 2 comma root 5, 3 comma root 6. Did you understand? Right. Sometimes what will happen is, in the previous context you have seen the domains are same, 1, 2, minus 3. Sometimes what he will do is the questionnaire to confuse the student. He will give with different domains. Of course, some common elements will be there. In such case, you have to first the intersection of the functions f and g, and you have to go for the calculations. It is most important. See, I'll give you one more example for that kind of situation. Say suppose f is equal 1 comma minus 3, 2 comma 8, 3 comma 9, say for a moment, and g is equal 1 comma 0, 8 comma minus 3, 2 comma 1, say for a moment. Then find f plus g, f by g, root f. Say we need to find f by f plus g, f by g, root f for a moment only. So now here you see the domain of f is 1, 2, 3. The domain of g is 1, 8, 2. So domains are different. So now you have to find the intersection of their domains. So domain of f intersection domain of g is equal, domain of f is 1, 2, 3, intersection domain of g is 1, 2, 8, 1, 2, 3, 1, 2, 8. So what would be the common elements here? Common elements in the two sets, they are 1 and 2. So now you have to calculate only on 1 and 2. Please do understand. So first and foremost, f plus g. So f plus g is equal f of x plus g of x. So now f plus g of 1 now. This is equal f of 1 plus g of 1. Here let us add, because we did not calculate f by g so far, let us add one more problem, f by g. So f plus g of 1 is equal f of 1 plus g of 1, which is equal f of 1 is minus 3 plus g of 1 is 0, minus 3 plus 0 is minus 3. And next value is 2. So f plus g of 2 is equal f of 2 plus g of 2. So which is equal, f of 2 is 8 from definition, g of 2 is 1, here you see, g of 2 is 1. That's it, f1 and 2. So now f plus g would be equal to 1 comma minus 3, 2 comma 9, the set of odd dead pairs. So this is the way you have to solve. Now coming to the next question. So f by g we took, no, I have not seen. So next question, f by g. F by g of x is equal f of x by g of x. Now f by g of 1 is equal f of 1 by g of 1, whereas f of 1 is minus 3 by g of 1 is 0, which is not defined. So you have to ignore this. Next, f by g of 2 is equal to f of 2 by g of 2, whereas f of 2 is 8 and g of 2 is 1. 8 by 1 is 8. So in this problem, now f by g is a singleton set, because 1 has associated with undefined element, so you should not consider it. So f by g is a singleton set, that is 2 comma 8. Understood? That's it. F by g, in this case you have to write 2 comma 8, ignoring this undefined situation. So coming to root f. Root f is equal, root f of x is equal root over f of x, as we know. So here alone you are finding root f, so f related value only. So here g is not involved. So it's not like f plus g or f by g or 2f minus 3g. So it's not something like that. It is alone f. So you can obviously you can take the domain of f, not that common domain. Understood this point? See why we took in the previous cases common domain, because once we found f plus g and another time we found f by g. So f and g both are considered in the function. So that is why common domain we have to use. In this circumstance, root f is alone involved. So you need not to go for that common domain. You have to go for only the domain of the function f, as f alone involved in this problem. So root f of 1, which is equal to root over f of 1, which is equal to root over f of 1 is minus 3, root minus 3. Root minus 3 is not a real number. So because it is not a real number, we only deal with a real function. So you have to ignore this case, okay, obviously. Next, root f of 2 is equal to root of f of 2, which is equal to root 8, which is equal to root 2. And root f of 3 is equal to root over f of 3, which is equal to root 9, which is 3. So here therefore root f, see this first situation you have to ignore, because you have ended up with a non-real image. You should not consider it. So only these two cases you have to consider. That 2 has image 2 root 2, 3 has image 3. So this is root f. You should strictly ignore undefined images and imaginary images. Understood? Thank you.